So that's me, and this is me. I'm not an expert on testing. I'm just a guy who, I don't like writing tests, but I have a stronger dislike for working on untested code. Especially my own code, because then I make really embarrassing mistakes that cost my employer quite a lot of money. I don't think anyone in the audience will remember the incident I'm talking about specifically, so let's not go into that. So basically, this isn't a talk I really wanted to give. It's a talk I wanted to attend, but since nobody was doing it, I decided I may as well give it a shot. And hopefully, there'll be some people in the audience here who will disagree strongly with some things I say and teach me how to do it better, because that's kind of my original goal. So, the very basics. What makes a test good? There are good tests and there are bad tests, and I'm sure everyone who's looked at test code can fairly easily tell the difference between this is a good test, this is a bad test. This isn't a definitive list or anything, it's just some things that I thought about and some things that I usually think about while I'm writing test code. So good tests in general are short, mostly because long tests are bad. If I can't see the whole, ideally the whole of a test, but at least the most important part of a test all on my screen at once, by the time I've gotten halfway through, I've forgotten what's at the top. And then it takes me longer to convince myself that the test is actually testing a thing that it should be testing. Good tests are also orthogonal. So each test case tests one thing or one code path or one kind of type of data or something, and there's very little overlap between tests. So if you have one gigantic test method that does 12 things, if the first one of those things breaks, the tests don't run for any of the others because your test already failed. And you can't tell from your continuous integration output, you all use continuous integration, right? You can't tell from your Travis build or whatever which piece of code you need to look at. You've got to then go and do some debugging and try and figure out where things broke. Another important thing is that good tests are clear and readable. If a test's obscure, it might be testing something, but how do I know? Maybe the test fails. I can tell that the test fails, but I don't know how to fix anything because I can't figure out what the test's actually doing or trying to achieve. And very important, good tests are documented. Just a little doc string at the top of a test method that says, this is what I'm doing, this is what the expected output should be, this is why I expect it this way, or something along those lines. So here's an example of a bad test. It's a toy example. There are a whole bunch of things wrong with this, and I don't think anyone would write this particular kind of test in that way, but I have written tests that are basically that kind of structure, but with a lot more stuff in them, which is worse because it's even harder to understand. So looking at that, I can't figure out immediately what's going on, and I wrote the thing. A good test, some reasons it's bad. Firstly, there's lots of test-specific setup. So there's self.operand 1, self.operand 2. Those are used in test methods, but who knows where. By the time they're used kind of down at the bottom there, you see, oh, it's self.operand 2, but what is the value of that? There's multiple things tested in a single method. In this case, it's just two things because slides with tiny flyspec2 code on them aren't useful. And the values in the test method are opaque. You don't know what self.operand 2 is without going back up to the top to see what it's defined as. This is a much better way to write exactly the same tests. these are the only tests on my slide that are going to have docstrings because slide space is limited, but all your tests should have docstrings. That kind of docstring, adding two positive numbers returns their sum, is probably not the best way of doing things, but it explains what it is you're testing. The purpose of the test is that you're adding two positive numbers and you get their sum, and then adding a negative number is equivalent to subtraction. Again, not a fantastic actual docstring, but it's better than not having anything. The purpose there is more to explain what it is you're testing and give some idea of why it's important, why that particular assertion is valuable to the code, what it tells me about the behavior that I'm expecting. Another important thing is that tests are damp, not dry. I tried to come up with a useful backronym for damp. The best I could think of is don't always make pasta. So this is one of the cases where good test code and good production code have sort of different priorities. This is a test that would have perhaps have been written by someone who's good at writing general purpose code, but not that experienced with writing test code. So there's a method, check deflector recalibration. Bonus points for figuring out which Star Trek series I was watching while I built these slides. And that encapsulates creating an object, running the code that you want to test, and then doing some kind of assertion. And then each of the individual tests just calls that with different parameters. I recently came across a much bigger, more complex example of this in some work code. It might have been written by me a long time ago or by a colleague. I'm not actually sure which. But it took me the better part of a day just to figure out what the tests were doing, never mind whether they were correct or not. Turned out they were correct, but that's not very useful if you can't tell that. Otherwise, you have to write tests for your tests, and then tests for your tests for your tests, and then you may as well write Java with the volume of code you're producing. So a better way to write that would be to have each test method being a little bit more verbose, but they each stand on their own. You can see test recalibrate deflector negative creates a thing, recalibrates it with a negative phase shift, and then asserts what the value should be. And it's obvious just by reading that single method which is on your screen in one place what's going on in that test. You don't have to keep bouncing backwards and forwards between the helper function thing at the top, which actually does the work, and the tests at the bottom, which provide the values for the various things. Another kind of random thing about tests is there are a whole lot of different test frameworks and test runners and all sorts of things. Which one of these do you use? Any ideas? Is there any clear winner over here? Yeah, basically, who cares? It doesn't matter. I personally like PyTest's runner, so I use it to run my tests, but I don't like all the magic it does with its assertions and fixtures and stuff like that, so I don't use those. I use standard library unit test stuff just because it's there and available. Unit test 2 is a much more comprehensive, capable version of the standard library unit test, which is in the standard library from Python 2.7, except I run Python 2.6 in production, so I don't get that. I dislike nose because I don't know if it's changed in the last couple of years, but Nose's test runner would use the first line of the docstring instead of the test name when it was reporting things. So in order to figure out where in your code the test failed, you either had to write the fully qualified method name or something as the first line of your docstring, which I'm not going to do, or you had to not write docstrings for your tests, which is what I did. And 5 or 6 years after I last really used Nosed for tests, I'm still trying to break that habit. So it's a vaguely rational reason for disliking Nosed, but it's not objectively bad, but one little thing like that, I can't use the whole framework at all. Trial is useful if you're running twisted code. You kind of have to, because trial's test case class handles deferreds and all of the good twisted stuff, which you kind of need to test. I used to use trial's test runner for non-twisted code until I figured out that PyTest actually gave me some more useful features. So tests don't kind of exist in isolation. This is the part that kind of picks up where all the "this is how you write tests" tutorials kind of end. If you've got a nice small piece of code where you can write tests like that and it doesn't interact with the rest of the world and all of that, well, writing tests is easy. What's the big deal? Most code isn't like that. At least most useful code isn't like that. And I'm not going to make rude comments about Haskell. So there are a bunch of things that you kind of need to be able to do to write more complex tests and set up more complex environments for your tests to run in. Some of these are things that already exist in Unit Test 2 and the Python standard library since 2.7, but as I said, I still care about 2.6. The first is setup and teardown. So everyone knows you've got a .setup method and a .teardown method, and you can create things in .setup and you clean them up in .teardown. But it's very easy to create something and then forget to clean it up because the creation and the cleanup happen in different places. So add a little add cleanup method, which just adds a function to a list, and then in your teardown, when your tests are done, it calls all those cleanup functions one after the other. The implementation is straightforward. I mean, that's the implementation I use in most places in my real code. It fits on a slide. It's easy. In Unit Test 2, there's an add cleanup with camel case instead of an underscore, which does this. I discovered that when I accidentally, well, I was writing this code and I used underscore cleanups as the list of functions, and my test runner exploded because unit tests basically add cleanup handler used the same attribute name and was getting confused with it not being what it expected because I overrode it. So that I found is probably the single most useful way of avoiding tests that leave the environment dirty, tests that don't clean up the database connections or don't close temporary files or leave network connections open and then make React fall over because it can only have 10,000 open network connections at once. Similar to that is monkey patching. If you look at the implementation, it's almost identical to the tests, the cleanup stuff. And usually I just implement it as a thing that does the monkey patch and then calls add cleanup to add a unmonkey patcher thing. This is also built into some of the test frameworks. Twisted has one. So if you need to replace some third-party library with a fake version or something like that, rather than manually monkey patching and hoping you return something to the right value afterwards and put it back and don't accidentally leave the standard library with some random fake implementation of socket or whatever. Yeah, use something that does the monkey patching and then queues a cleanup afterwards. So these are kind of general things. Now, if you've got non-trivial code, you always end up with your custom assertions. Usually that's a method on your test case class, which is .assert my favorite color is red or something. The problem with those is that they're tied to a particular test case class. So if you need them in multiple places, either you have a common base class which everything inherits, or you have multiple implementations of this, or what usually happens in a lot of code bases I've worked on is you have some random combination of both. And then you've got something that behaves in one way in most of your test cases, but a different way somewhere else, and then you think you know what your test's doing, but actually it's a lie. And then you spend a week trying to debug tests that are passing when they shouldn't, or failing when they shouldn't, or something. So test tools is a library that provides a bunch of things, but what I consider the most useful is a generic matcher thing. So instead of writing a custom assertion, you write a matcher object, which this is actually a completely valid test tools matcher object. The important thing there is basically the match method, and it's basically what your assertion does. It checks to see, does this observed object I've been given meet the requirements? If not, it returns a thing that says, no, it doesn't, and explains why. Otherwise, it's otherwise it just returns none, and you can assume that the matcher succeeded. And then at the bottom, instead of calling your own custom assertion, you use assert that, you give it an object, and you give it a matcher. And the thing about this is you can have a whole bunch of different matches that test things that are common within your system, but don't necessarily occur everywhere. And then you can use the matches you need to use in kind of way you need to use them, and you don't need to have a common base class which has 10,000 assertions on it, most of which are irrelevant in most places, or have almost but not quite the same duplicated code everywhere. More along those lines is, along with custom assertions, you often end up with custom helper functions. So give me a pre-constructed object with these parameters, or something along those lines. This is generally worse than the assertion case, because often these things need to set up potentially expensive objects. Maybe it needs to push a bunch of stuff into a database, or create some complex object which is connected to other objects or something like that. Often you need to do some kind of cleanup, and the cost of having this kind of helper being invoked in places where it's unnecessary can be high. In some of my code, we've got a helper which sets up a whole bunch of objects in a local React server and creates some stuff in a Django database, and then just waits in case you need to use it. And then at the end, it tears it all down again. And our test runs were taking 10, 15 minutes. After switching to something like this, where it's much easier to only pull it in where you need it and not have all sorts of things just on a base class because it's convenient to have them there. We didn't quite cut the test run time in half, because it turned out that most of the places we were using that we actually did need to use it, but it did cut something like 20 to 30% off our test run time, and made my CPU fan a lot happier because I wasn't doing huge amounts of unnecessary work. So that's basically it's a very simple toy helper, but the general structure is you create a helper with maybe some default parameters. It has a cleanup thing which may or may not be empty. In this case it is because it's a toy. And then it's got some methods on it that do stuff. I can show some real ones later if you're interested. And then you use this basically by, in your setup, you create a helper. Doesn't have to be in setup, can be in a test method if only some of your tests need it. You add the cleanup for it so that you know that it'll be cleaned up properly. And then you use the helper instead of calling self.getDeflector or whatever in various places. The other nice thing about this kind of more complex helper is that you can combine them. So in my case, I've got a thing that handles general persistence, and then built on top of that, there's a thing that handles accounts, and then built on top of that, there's a thing that handles various other objects which happen to require accounts. So I've, instead of having all sorts of things that just call a spaghetti network of helper methods, which is what I had before, I've got an object, say an account helper, which creates a persistence helper, or you can give it an existing persistence helper if you already have one, stuff like that. So yeah, that's helper things. One of the things you often need to use helpers for and stuff is other parts of the system. Code doesn't live in isolation. If you're writing some piece of code, you probably need to talk to some other piece of code or some external system or whatever. So you need test doubles. A list of terminology. This is the most consistent set of terminology I've seen. I got it off Martin Fowler's website, and he credits someone else who wrote a book, and I can't remember the name of the person who wrote the book. He doesn't mention recording doubles in that particular post, I think, or maybe he does, I forget. But going from sort of least complex to most complex, the first kind of test double is just a dummy. It's a placeholder. It doesn't have any behavior. Something needs a parameter, so you give it a parameter. A stub is slightly more complex than a dummy. Usually it's something similar to a dummy, but it needs to do something. It needs to have a particular attribute or a particular method that returns something. Then there's a mock, which is kind of like a stub, but much more generic and general. Is anyone unfamiliar with the Python mock library? Okay. It's a tool that, there'll be an example later, but it's a tool that basically lets you create an object. You say foo equals mock.mock, and then you can just call methods on it and look up parameters and all sorts of things. And then at the end, you can assert that various things happened and parameters were a particular value and all sorts of things. It's really useful for kind of verifying that particular functions and methods were called in a particular order at particular times. More on that later. And then a fake is kind of, it's more specific. It's basically an alternate implementation of a thing. So in my case, I might have a fake that it looks like an account store database thing, but instead of talking to databases and React and APIs on the internet, it just keeps things in memory. And you tell it, create an account, and it says, yes, I created it, and it puts something in a dict. and you ask it for an account lookup, and it just gives you whatever it has in the dict. That's generally harder work to build, but it's kind of has various advantages over mocks. And then something that's slightly different is a recording double. It's more specific. What it does is an HTTP API kind of thing is kind of the canonical example. You make a call. You say, I want to hit this URL with these parameters, and it makes a note of that, writes it down, makes the call, gets the response, writes down the response, and then gives you the response. And then later you can run it in sort of offline mode, and it uses that stored data to kind of match and return the whatever the real requests and responses were earlier.
So
yeah?
you save that data with the code base?
It depends. There are various... what you do with the data can depend on what the data is, but I'll talk about that a little more. So some examples of each. Dummies are really simple. The most common dummy in Python is probably just none. This thing needs a parameter, but it doesn't do anything with it. Well, none is a handy value. Sometimes a string is useful. Sometimes you might care that a particular object is actually being passed somewhere. So you can use an instance of object and then later on assert that the object you're getting back from something is the same one that you gave it. Nothing particularly complicated there. A stub, in this case, you've got an actual object which has, it's the simplest possible way of doing this thing. You tell it what you want the status to be and set the attribute, and then in your test you call your test code with an object which returns something that some value that you know, and then you can make assertions that your, in this case, query engine status is doing the right thing with the something that is inside your stub object. Mock. This is an example of, I don't know how well you can see the difference in background color, but basically this big gap over here, this over here is the real code, the code under test, and this over here is the test code, and there's sort of a gap between them. So in this case, it's worth noting that in your test where you're using this mock, you're never actually doing anything with the deflector object up at the top that your code under test is touching. So this test is fine now. It validates that recalibrate deflector calls the right methods on the deflector instance with the right parameters. But what happens if you add another non-optional parameter to the shift phase method? Your test continues to pass, but your production code will break because your mock and your implementation have diverged. So you have to be really careful about using mocks in this way. There are places where it's useful, but in general, I've found that every time I've used them, I've run into trouble at some point. So a similar thing using a fake implementation. That is an implementation of, a different implementation of the real thing you're testing. The thing about a fake is that you can write it once and use it everywhere you need to test something that interacts with that particular part of your system. So it decreases the chance of your tests and your production code diverging because you only have to maintain the fake in one place. You don't have to run around your test finding places where you're mocking out a particular thing and checking that the mocks are up to date and whatever. And that brings me to the next thing, which is a verified fake. the difference between a fake and a verified fake is that a verified fake is verified. You run the same set of tests on your real implementation and your verified fake, and assuming that your test coverage is sufficient, you now have a guarantee that your real implementation and your fake implementation have the same behavior. And if your real implementation changes and your fake doesn't, one of those tests will fail, and you can see, oh, my fake's different now, I need to go and fix that. I really wish more people used verified fakes because I want to fake out their libraries. If someone writes a library to do something and I'm using that library, I can't easily write a verified fake for their library because I have to basically re-implement all of their tests and run my own test implementations against their code and stuff like that, and it becomes really hard to verify. So I'm trying to kind of get into the habit of writing verified fakes for bits of my code for which it's useful, so that other people using my libraries can test how their code interacts with mine without having to have a database connection or a React server or something like that. And then the recording double I've already kind of explained. It records your requests and responses, or your function calls and parameters and the responses and whatever in record mode. And then in playback mode, it asserts that the request you're making is valid. Sometimes you might want to assert that requests are being made in a particular order. Sometimes you don't. And in playback mode, it also gives you the stored responses back, so you can run tests that aren't dependent on having the internet accessible and production credentials in Travis that let you launch EC2 instances to test that your EC2 instance launcher works, that sort of thing. I've got a real example which may or may not be useful. It's fairly specific. It uses a library called Betamax, which records and replays. It hooks into the requests HTTP library. The name is because it's a port of a Ruby library called VCR. I think the pun is that it's technically superior but lost. It has a bunch of problems. It doesn't do some things that I want it to do. Specifically, it's hard to tell it not to store certain kinds of data. Like the API I was using it for, I can have it use placeholders for my authentication credentials because I know those ahead of time, but I can't tell it not to store the session cookie that the response returns, which is valid for 2 hours. So if you watch my GitHub commit logs and I don't wait 2 hours or modify the stored data before committing, you might be able to grab a valid session cookie for my API and then do something nasty on my test account, which won't buy you very much, but there might be other more dangerous things out there. Also in this particular API, it returns a bunch of personal information about account holders, and it's a test account, but the information about me in there is the same as the information in the real account. So you get my cell phone number, which it uses for some kind of authentication or verification or whatever. And I don't really want to have my cell phone number and a session cookie and all sorts of things in test data, which is in a GitHub repository, which is public. And that's the end of the slides. So there's still, I think, about 20 minutes or so left. 8 minutes, okay. Oh, right. But we started at 15:15, not 15:30. So now you get to ask me questions. And hopefully ask me questions that you know the answer to, but I don't, or something. Yeah?
How does Betamax get a fund load? Because I use fund loads.
I haven't, so I can't comment. I've written my own recording double implementations 2 or 3 times, and they've always been fairly closely tied to the code that they're testing. I used Betamax because I had a deadline recently, and Mike Jones would have been unhappy if I'd spent 3 weeks writing a recording double framework for code that he needed tomorrow. Yeah.
It's mentioned, I haven't tried using it, but I just did a quick search on Google. It looks like there is now a plugin from those which will make it report the name of the test instead of the doc string.
There was one a while ago, and I read the implementation for that, and it terrified me. It basically, by the time the plugin got the test, the information had already been lost, so it had to go and figure out where the test came from by digging through stack frames, and then it rewrote the first line of the doc string for it. Yeah, I tried it, and it kind of worked, but it wasn't quite good enough for what I did. These particular tests, I used decorators and stuff, and meta classes, and I built copies of tests for. So the thing I was testing was a domain name reselling system, and we had a bunch of different domain name registrars on the back end, some of which supported some features, some supported others. So I wanted the same tests run against everything that used the common feature set. So each test had a list of backends that it would be run against, and I generated tests for that. So they all had the same doc string, but they were different tests for different bits of the system. Yeah.
Okay, so obviously I'm guessing a lot of people here have intended to write test code, might have gotten to 2 lines and then hit the deadline. I've specifically got a case where a bunch of data gets inserted into a DB. This works with an API, and then there's a call that processes the data and populates a bunch of other tables. Would you rather mock the whole database, or would you rather have your, I'm guessing these continuous integration things, which I fully intend to use at some point, does that allow me to have kind of a test DB that I can say, okay, restore this DB, do the run on it and compare it to some DB, or what would you do in such a case?
It depends on what the code's doing and the structure of the data and that kind of thing. Talk to me afterwards and I can hopefully figure something out. But if your code is in GitHub and it's got tests for it, continuous integration through Travis is basically 10 minutes to set up, which includes sitting waiting for crappy internet to load your login page and stuff like that. So if your code's in GitHub, there's no excuse for not using continuous integration. If it's not in GitHub, it's slightly harder, but only slightly.
So,
yeah?
Based on your description of mock.mock, it sounds like mock.mock is complete. You really should be able to set it a class, and so you can try to mock that specific class. The whole function in Python does a good job of analyzing the class structure and what the input-output is supposed to do.
You can do that, but my experience is it's really hard to use it safely. And also that tends to be everything, all your stuff being mocked and whatever per test, which means that when stuff changes, you've got to go and find the tests that need to be updated. You can't just go to your fake implementation and update that. So it is possible to use it in a way that's not particularly dangerous, but it's also possible to write clean readable Perl. I have seen it done. It's rare. Yeah?
No, but the idea is that if you write a class, then you should provide the users of your class with an SQL mock as well.
Yes. Ideally, that's what the verified fake is. It's a bunch of work. It's a trade-off. a lot of things, the implementation is simple enough that there's no value in a fake, just use the real implementation. But if using the real implementation is expensive, there's a database or external calls, or it calculates the 50,000th digit of pi or something like that. A fake or something is generally a better idea. Yeah?
When you talk about verified fakes,
Yeah.
what's the point of that exactly? Seeing as you have to do the whole setup and stuff within the test, so you're not going to avoid the expensive stuff.
So you're testing two different things. So the verified fake, you're running the test with the tests for the object that you're faking. So my account store, I have a set of tests that runs against the real account store, which sets up databases and all of that, because that's the code being tested. And it runs those same tests against the fake. But then in my tests for some other piece of code that just happens to use the account store, that uses the fake as if it was the real thing. So then instead of setting up a database, I added entry to a dictionary, and that's much cheaper. Teardown, I don't need to go and delete rows from databases and stuff. I can just throw away a dict.
Sorry, but
Yeah?
since you're doing the verification of the fake already, wouldn't you already have the MDB there for you to use in some other code? You wouldn't need to have the fake in the first place, because now you've already
Yeah, but the
work's been done.
the data, the number of accounts and the type of things in the account and whatever would be different. So I can't just use the same, sort of like a copy of the database file or something. And also it might not be a database. It might be talking to a third-party API. It might be something that's generally non-deterministic, but the fake has a deterministic kind of implementation. Often the fake does have some kind of extra hooks, so you can initialize it with specific data that you can't easily do in the real thing. So in my account store fake thing, the real account IDs are UUIDs, which are generated at account creation time. The fake generates a sequential set of account identifiers. So I can verify much more easily that this belongs to a particular account without having to do a bunch of jumping through hoops. Okay, get this account identifier, look up something else, make sure it's the same thing.
Do you have any final questions?
If I could give an observation.
Please.
I've noticed that a common structure of Python unit tests is to have a big class with a bunch of tests, functions in it that all kind of do the same setup and add teardown hooks, whatever. And they can get quite messy and you end up with these monstrous classes. It can make a lot of sense to have smaller classes that have a setup function that sets up everything that's needed for maybe 2 or 3 tests only. So you have a lot of little classes that set up the same. It also means you don't have to have multiple asserts in each test function, because you've got the majority of your code actually in a setup and teardown, and only a tiny amount of code in each test, which is a couple of asserts.
Yeah, it's basically a style thing.
I think your style leads more towards little helper classes everywhere.
Yeah, well, for my particular helper classes, I can show people who are interested afterwards. The code's all open source. I've got a few big helper classes, and then my tests are generally split up one class per thing I'm testing. But there are a bunch of places where I have 2 or 3 test case classes for a thing that I'm testing because I'm testing different aspects of it, or
That's what I'm getting at.
yeah. So how many of those little classes you've got and whatever, that's a style thing. It's a trade-off in various directions.
If we can say thank you to Jeremy again.
Thank you.